All right, good afternoon. I'm Rick. This is parallel programming for C++ developers in Visual Studio 2010. Today I want to talk a little bit about the motivation and some of the hard problems that we see developers facing. We'll quickly move from that into what we're doing about it. First I'll talk about, more generally, what we're doing not just in C++, but across the company and across Visual Studio. And then we'll spend the rest of the time talking about Visual Studio 2010, the CTP, and what we're actually doing in our C++ development platform. We're going to talk about the parallel pattern library, which is a library for expressing tasks and for working with collections concurrently. And we're going to talk about the asynchronous agents library, a data flow message passing library. And finally, we'll also talk about the concurrency runtime. So this is a new platform component that we're working on that will help manage the concurrency and unlock the scalability in the platform. Along the way, I'll also show some of the debugger enhancements and a couple of, just a minute of some of the profiler enhancements. I know several folks here came from Hazem's talks just a few minutes ago, and I know there were some questions. So when we talk about parallel computing, particularly on the desktop, there's a lot of problems that are in the space right now. We know, and we've been told, that the hardware is actually moving beyond single-core performance and is actually moving towards many-core scale-out. So rather than faster and faster single-processor boxes, we'll see additional improvements being delivered through increased die count on the chips. But this creates some problems for us, the developers. One of the primary problems is that it's just really hard. When we talk to companies, they think that maybe 5% of developers, maybe 10%. Very few numbers are actually successful and have the skills to write multi-threaded code today using the APIs and the tooling that is available. Next, we need to actually manage that concurrency that's actually there on the platform. And building an application once and deploying it and having it scale well on a single core or a dual core or a quad core or an 8-core, all the way up to many core, is not something that most people should have to spend time worrying about. But it's a very real new problem that's coming up. And finally, in addition to managing that concurrency and expressing those problems, we actually have to deal with the correctness issues, deadlocks, live locks, races, all those things that come up once we start building serious multi-threaded code. Once that happens, then we can start enabling all developers to actually be very productive at developing parallel code. And it doesn't matter whether you're in C++ or C# or VB. Right? This is about all developers. Here's a very simple example. This is C++ code. It's just a simple, naive matrix multiply. No one would ever do this for multiplying matrices in real life. But the interesting thing about it, of course, is that the outer loop is very embarrassingly parallel. But if I were to hand use threading APIs to do this, it's going to take a lot of code. Right? I have to deal with partitioning the data and synchronization. There's a lot of boilerplate code. And somewhere down in here is actually the code I care about, right? That little tiny bit. The rest of this is all infrastructure and scaffolding. But we don't want folks to do this. Instead, now I'm on my quad-core laptop. I'll be doing several demos from here, and then we have a 16-way that we'll be looking at a little bit later as well. So here's that same code. Here's a library call in the parallel pattern library called the parallel 4. One thing you'll notice is that I'm using a new feature from C++ OX. And this is something that's actually in the CTP as well that's on the hard drives, called lambda support. So I'm going to go from 0 to size and increment in steps of 1. And here's the lambda definition. I'm going to capture the stack by reference. I'm going to pass in an integer and call it j. And then the curly braces declare the lambda. And now I need to actually close my function call and build it. So let's run this. Here we're multiplying a 500 by 500 matrix. Ooh, that's not good. We got a 2.7x speed up. Let's do that again. Okay, 2.9x speed up. So what we should do is probably look at that in the profiler and see what's going on. Usually it gets about a 3.7 to 3.9x speed up on this box with that. But this is a demo and a talk, and all demos must break. So, anyways. But we know that the domain is much broader than a simple parallel for, right? We have what we call imperative data parallelism, task parallelism, which actually parallel for is an implementation of. Dealing with shared resources, of course, declarative data parallelism, and asynchrony. And what you'll see is Microsoft is actually working on a series of technologies to help with this. In the managed side, we're working on the task parallel library. On the native side, the parallel pattern library, which I'm talking about today. Of course, OpenMP is already there, and there's cluster SOA as well. Additionally, both across managed and native, we're working on a set of coordination data structures, so you can actually take a collection and add things to it, or remove things to it, or iterate it concurrently. And in the future, we'll be looking at solutions like transactional memory, but that's pretty researchy right now. For data parallelism, in the managed side, there's this wonderful thing called plink, right? So if you're familiar with link, plink is just link in parallel. And Daniel Moth will be talking about that at his session. I think it's on Wednesday. And of course, we have, for asynchronous programming, we already have MPI and MPI.NET, the CCR, which is a managed offering, and I'll be talking about the native agents in messaging library. And then the way that these get delivered to all of you, right? This isn't just about the desktop, and it's not just about the cluster, right? It's actually a spectrum. And as we move from task-based parallelism to pure data parallelism, where you're, say, taking a loop and applying the same operation on multiple sets of data, we'll see some technologies available now and some technologies available in the future that actually help the spectrum. So, all right. So that's about it for the setup. Lots of techie stuff for the rest of this. So I want to start things off with a demo application that I'll refer back to a couple times. This is a simple image processing pipeline. It's interesting because it's not just a parallel for, right? It has some I/O. It has some nested parallel fours that can actually work together. And then we have to actually communicate with a file system or display. Specifically, what we're going to be doing is we're going to be looking for image files on a directory. We're going to be loading those images from disk, applying some image filters to them, and then rendering them to the screen. So let's take a look and see what this looks like serially. So the filter that I'm running, it's going to take some time. So it's found 28 images. And what it's doing is it's first applying a Gaussian blur to things to sort of smooth things up. There's a mix, too, on the share. Some of the images are large and some of them are small. After the Gaussian blur, it's actually going to do a high-pass filter and then an additional blur of that and then combine them, right? So some of these blurs are actually expensive. Some of them are cheap computationally. The effect is something sort of like the glow in Tron, if you can see this a little bit. And it'll take a very long time to run this. So I'm just going to let that go. And we'll come back to it in a few minutes as we actually parallelize it. Oh, no. What happened here? Sorry. And we're going to start talking about the concurrency runtime. Here we go. This is the whole stack. We've got the concurrency runtime, as a layer where we have a task scheduler and our resource manager. And then in the programming model, we have the parallel pattern library and the asynchronous agents library. We'll talk about the runtime first. There's a couple of key concepts that are sort of grounding to the way that the runtime is built. First of all, it's a load balancing scheduler, right? So this isn't just pure static decomposition, but actually being able to adapt to loads over time as your application is running. Because as we know, there's other things running on the system, right? And it's just not so easy to actually express that concurrency and do that partitioning at design time. The other thing we'll talk about is dynamic resource management. And so this is being able to take competing requests from multiple concurrent components within an application and actually arbitrate between them. So if I have one component here which is running in parallel and another component here that's running in parallel, when they're both active at the same time, I'd like to split up the machine cooperatively and equally, right? So that I'm not spending any time with cache coherency or those sorts of things. And then when one of them dries up, I can actually take those resources and apply them dynamically to the other one, so it will actually have full access to the machine. And this is just a little picture to help us think about load balancing, right? So if on the left I'm talking about static partitioning and each of the blocks is a chunk of work, you can see that at static time, it's actually hard to schedule these, but this is somewhat constructed, and I can actually schedule them more efficiently and have the entire system be done faster. And when we talk about the functionality that the runtime has, I'm going to talk about it at a high level. Nicholas Gustafson is talking on Thursday, I believe, and he'll be going at it in a more detailed manner. I'll spend most of my time on PPL and on the agents APIs. We talk about the platform infrastructure for the concurrency. So this is providing a low overhead scheduler so that you don't have to worry about that and you can actually focus on your domain problems. Talking about cooperative blocking. So as an application, I may be doing some call, like going out to the web, where I know I'm in a block. I can use that as an opportunity in my application to actually run something else. So that support is actually deeply built into the runtime. And we'll have locking primitives and synchronization primitives plus programmer control over actually expressing that. And then finally, support for multiple scheduler instances, right? So something that's been missing is the ability to actually have that application with multiple concurrent components and declare this component has some quality of service needs and I'd like it to take up X% of the system or run at this priority, right? This other component is something that can actually do well on the whole system, so please let it have the whole system. And actually be able to be very declarative about that, be very precise, but still have forward-looking scalability for future platforms. And of course, resource management, which I mentioned. And so this is a way to actually ask for these schedulers, for the resource manager to actually arbitrate between them and adjust them dynamically at runtime. And then finally, platform extensibility and composability. So this is key. So in addition to the programming models we build, we know that there's going to be additional programming models and additional libraries. And what we want actually is to enable the community to actually build on top of that, right? So as you're building your library or your component, you can actually let the resource manager know which resources you're using. And it can then adjust between the other components used and the other libraries that are actually built on that system. And one of the exciting things that actually was announced at Intel Developers Forum probably about a month and a half ago now was that Intel mentioned they'll be taking their Parallel Studio, so their threading building blocks library, their OpenMP support in their compiler, and their development tools, and they'll be porting it to the concurrency runtime. And what this means for you is that the platforms are actually going to scale. So if you're using TBV and you're using the PPL on the same application, they're actually going to compose and perform well together. We're also going to work on aligning the interfaces. So TBV has also agreed to ship some of the interfaces in the PPL, and this will reduce the concept count, right? So the techniques you're learning with PPL will actually be applicable in TBV. And that's actually incredibly valuable, because we can also then iterate on them and get broad adoption and actually move the whole field forward. Because these concepts and these libraries need to actually be embedded pretty deeply in the language for us to be really productive. And this is the start. Great. Okay, so the parallel pattern library. This is a programming model for task parallelism and for parallel algorithms, and we have some synchronization primitives and data structures built into it. What we want to do is actually simplify the process of writing parallel applications so that you have these abstractions that aren't threads, that aren't mutexes, right, that aren't schedulers, but actually a parallel for, as we saw before, or a task. And we also want to build in composability so that you're not actually describing scheduling semantics as you're building your library. You might actually have something like a parallel for with a parallel sort composed together, and then you want to really late bind that quality of service so that your customers, perhaps if you're a library developer, could actually describe that concurrency, or your application could describe that concurrency when it needs it. The fundamental concepts in the parallel pattern library are twofold. First, the task. This is just a description of some work that can be scheduled and run. It's very straightforward. We call it a task handle. The second abstraction is a task group. And this is actually a collection of tasks that form a logical computation or subcomputation. So you'll describe a series of tasks as task handles. You'll actually express them, schedule them, and wait for them with task group. One of the key things that's actually incredibly important with this concept is that in addition to scheduling and waiting on them, you can also cancel them. We'll have extensibility methods so you can actually extract exceptions out of them, right? You can derive from them and add additional functionality on top of them. It's very primitive and very flexible. Most of the PPL is actually built on top of the task handle and the task group. So here's a simple example that's great for task parallelism. This is just a recursive quicksort. Again, the nice thing about the quicksort is that I can partition the data, and then I sort the left side, and I can sort the right side. Then I wait for them both to be done, right? I can express this with the PPL's tasks by declaring a task group. And in this case, I'm just using an implicit method for taskgroup.run. And again, I'm using a lambda here to describe the left side. I'm using a lambda to describe the right side. And then I'm just calling g.wait on my task group. It's very straightforward. And let's look at debugging tasks. So one of the things that's going to be here, and great. So let's go back to parallel matrix multiply. As I mentioned, the PPL is built on tasks, so we can actually look at the tasks in this. We have two abstractions for debugging tasks in Visual Studio 2010, and I believe they're in the CTP. Yes. The first is a task view, which will, rather than giving you a thread view, right, it'll actually give you a task view. It'll let you look at the abstraction that you're expressing things in, rather than the underlying threads. The threads are still there, right? You can still navigate around them if you want to and look at the call stacks, but this will show you all of the tasks that are currently on the system. The second view is a multi-stack view. And this is useful both for multi-threaded views and for task views. And so this will actually give you a larger overview of your application and show things in an upside-down cactus stack. And I'll just show it to you in a second. So let's start this in the debugger. So here it is, the task view. I had it just kind of buried down there, right where the thread view usually is. Here you can see I have a series of tasks. I've got actually 4 running. That's great because this is a quad-core machine. You can actually see their call stack. These 2 are actually in the middle of a lambda. And then these are the additional tasks that are actually scheduled, right? So I have about 10 tasks that are scheduled that aren't currently running. And down at the bottom, you can actually see that 2 tasks are waiting. So when we talked about cooperative blocking, as a task blocks, as you call wait on a task, you can actually see that expressed. And let's see if I can do this. If I take this, you can actually see the stack changing underneath. Did you guys catch that? It'll actually navigate the call stack to where it is for that task. So the second view is a multi-stack view. Great. So here's the tasks view. You can actually see the parent tasks and their children's. Parallel 4 in this case is actually implemented through a series of tasks that have children that are scheduled in this way. And then you can see where they're at in the stack. You can also look at the thread view. And here's this little command view, so you can zoom around. We've got the active stack highlighted. I can actually click on this one, right, and switch the frame to that stack and then go back. You can go up here. I can see how many threads are actually blocked in this stack. It's incredibly useful for a more complex application. This one doesn't have very much to it. But even the imaging demo has many threads actually running and many components going on at the same time. So, great. All right. So let's talk about algorithm support in the parallel pattern library. One of the key things we wanted to do was really enable broad adoption and enable familiarity. So we'll have STL-style algorithms for compatibility and composability. So this means that the algorithms that we provide will actually provide iterator support. They'll have signatures that match where appropriate with the STL, and they'll have similar naming conventions and similar semantics. Some of the semantics will be adjusted for parallelism. So we have parallel 4, which we've seen before, right? Which is just an iteration over an index range. It's a template function, so actually anything that supports the ++ operator and the divide operator will work. It'll work great with longs and ints and int64s, right? You pick. Well, parallel for each. So you can take a vector and actually iterate over it, right? You can actually abstract that vector and pass it a list and iterate concurrently over that. We'll use template specialization for that, right? Rich iterator support, incredibly important. Parallel accumulate. Folks more familiar with parallelism tend to call this reduce. But this is actually a pretty fundamental algorithm, and it actually enables many other algorithms in the STL. In Nicholas's talk, he'll actually talk about extending the PPL to include parallel accumulate. It's not something that's in the CTP at this time, but it's something that we're, considering for a future beta. And again, on accumulate, we'll have both methods, right? So you can use the built-in std+, or you can actually provide your own operator for that. And then parallel invoke. So I could have used parallel invoke with quicksort. Really, this is just take a series of functors, execute them, wait for them to complete. If there's an exception that happens in that, we'll actually marshal that and extract that out. Same thing with the tasks. We'll actually marshal it and extract it out on the joins or the waits. All right, so let's look at our imaging demo. Let's go back to it and see how it did. Oh. All right, 191 seconds. Long time. Well, here it is. Here's the call right here. So this is the serial work once I actually find files. I can actually add parallel 4s to these. So I have these two functions a sequential Gaussian blur, and a sequential glow filter. I have them already built. We can rebuild this. We can go look at it. And you can, in fact, see that I've taken this parallel 4 here in this parallel version. Note that I'm actually using slightly different capture semantics in the lambda. This is something that's a little different for folks that are familiar with C# delegates. The C++ lambdas has pretty rich capture semantic support, so you can capture by reference and capture by value, and you can take a copy and actually make it mutable. So let's run this. This will be on the quad core, but the performance isn't that different from the other box. So this still isn't quite enough to make a difference. Things got a lot faster, but it's not quite enough. We'll get back to it when I talk about the agents library. So for synchronization and shared state, data structures, locks, and concurrent objects. Cooperative synchronization primitives. So mentioning cooperative here in the context of locks, when I take a lock and I don't get it, the runtime is aware of it. We can use that as an opportunity to run something else. So the concurrency runtime and the parallel pattern library will have a set of locks built in that are cooperative. We're looking at a critical section called intercritical, a simple reader writer, and of course, C++ OX is adding std mutex. So at some point, that will come online in the future. One of the things that's interesting about the locks we're building is they actually support the C++ OX mutex requirements. Right? So in addition to std mutex, there's a set of requirements so that if your lock supports lock, try-lock, and unlock, then there's some utility functions you can use on that. And the locks we're providing, the cooperative versions actually support those. So you'll have that composability and that compatibility there. And then concurrent containers and objects. So we'll talk about something called combinable, which is really a generalized reduction variable that can provide thread local reusable storage. This isn't in the CTP, unfortunately, but I have the next few slides talking about it so we can actually look at that. We can talk about a concurrent vector. So this is very similar to the vector that's in the STL. It's also incredibly similar to the vector that's in TBB, if folks have looked at that, and shares similar semantics. But it supports concurrent append and random access iteration. So things it doesn't support remove. Right? You can, of course, clear the whole thing. But it's intended to be incredibly efficient to have that random access append. Talking about a concurrent queue, which again supports concurrent append on the front. It's got forward access iteration. They're likely going to be unsafe iterators, so we're probably not going to support you adding to it while you're iterating over it. But there will be iteration support there. And we've changed the semantics for actually adding to the queue from the C++ and the C++ OX semantics where it was a two-step operation to a single-step operation. This is actually another place where we're very similarly aligned to the managed side. So we've taken the opportunity to actually align where possible on the concepts and on the APIs as well. And then a concurrent unordered map. So concurrent insert, forward iteration. Again, the containers, unfortunately, aren't in the CTP. The locks aren't in the CTP, but these are the things we're thinking about in the future. So let's look about combinable and talk about why we care about it. So here's a simple for loop. I probably should have used for each, but I used for here. In the most trivial sense, I'm actually going to add a value based on some computation to a variable. If this was just one value, of course, I could use accumulate. But if I had multiple values in here that I was accumulating on, clearly I wouldn't be able to do this, and I'd have to use something like an interlocked increment if it's a variable that supports it, or a lock or something like that. But what I can actually do instead is declare a combinable object. So combinable is a template object. It's going to provide a reference to a local object. So here's my local sums. I'm going to capture it in my Lambda. And then I'm going to, in the body of my loop, I'm actually going to get that local value and append to it. And then I'm going to call this combine function, giving it std plus in this case. Right? So this is a very simple example of how to use this. But there's some other more interesting examples. Here's a vector of images and a list of results very similar to the imaging demo. If I want to do an iteration over the vector, load that image, and then add it to the list, that's great to do it in serial, but I can't do it in parallel, right? Because list wasn't on the container list that I said. I don't have a thread-safe version of it. I could build a coarse-grained block one, but that would potentially be unperformant. But I'm going to build a combinable list. So this is now a combinable list of image star. And now I can iterate over that vector. And I can add on to the local copy of that image list the current image after I've loaded it. The nice thing about std list is it offers the splice functionality, right? So you can take a series of lists and combine them together into one list. And so I'm going to do that. I'll just call combine each. Take each of the local images, combine them together. The third use case for this that's incredibly valuable is for an object that's incredibly expensive to construct, but cheap to reuse, right? So if I have a large iteration or a large concurrent object, I can actually take a combinable object of that. The first time I use it or access this local member, it'll actually construct one. And then when it's used again on that same thread, it can actually reuse that. So, make sense? Great. All right, so just, again, summarizing what's in the parallel pattern library. So we have task parallelism. We have some algorithms. So you can speak in terms of tasks. You can iterate over loops. You can potentially take some of your existing loops, which are computationally expensive, and port them and make them scale better. We have synchronization primitives so that when you have to deal with shared state, you can do it in a way that's actually cooperative and that lets the runtime know that you're about to block so that other things can be run. And we have concurrent containers and objects for actually collecting up items, working with groups of them, and actually doing things concurrently. And of course, everything on the right-hand side, the synchronization primitives and the concurrent containers, they work great outside of the PPL2, right? The center critical lock, it's a lock, right? Even if you use it in your regular application that isn't using any of the constructs, it's going to be correct. The vector will be thread safe. You can use it outside of the parallel for each, right? So wherever you're going to use it, they'll work. It's incredibly important for migration and compatibility. All right. So the asynchronous agents library. Providing an alternative to shared state. One of the core foundations of the agents library. Message passing has this sort of unique trait where if you can actually afford to copy the messages, you don't have to worry about the shared state, right? Because I can take an object, I can copy it, I can do something to that, I can transform it, I can copy it again. And there are several data flow libraries now. One of the things that's interesting about this data flow library is it's concurrent, right? So we're all very good at building things like decorators and pipelines, but constructing them and having them be automatically concurrent so that when you pass that message to that stage in the pipeline, a task is scheduled and run at the next available opportunity without having to do anything special or fancy or write any locks. That's what this does. And it gives you a safe place to start, right? So we can stay in a world where we're copying by value everything, and it's nice and safe. If you want to actually, for performance, add some pointers, take care to be careful with them, that works too. It's the template library. But we can give folks a safe place to start and avoid that shared state whenever possible. So the key concepts in the agents library, we'll talk about an agent. An agent is a base class that you can derive from. It's a pretty large-grained, coarse-grained construct in your application. It tends to have inputs that you'll send messages to. Perhaps it has a network inside it, does some work on it, and has outputs that you can receive from. These would be very high-level constructs. The imaging demo has actually one agent in it, and it acts like the controller, essentially. And then we'll talk about sources and targets. So a source is something that generates a message, and a target is something you can send a message to. It's really that straightforward. And we'll talk about cooperative send and receive. So again, cooperative, so I can receive a message from a source. That receive will be cooperative by default, and it will wait until there's actually a message there. Right? So I can actually start declaring that network, constructing it at design time, and then activate it when I start sending messages or turn it on. And we'll talk about cooperative send. So actually sending a message, making it sure it got to the buffer. Not that it's propagated out necessarily to everything in the network, but at least gotten to the place it was intended to go. And non-blocking versions of these, so an asynchronous send and a try receive, right? So you don't always have to block. So we have a set of core message blocks. In the CTP, we have an unbounded buffer and we have an overwrite buffer. Single assignment is not in the CTP. An unbounded buffer will just take as many messages as you can send to it until you run out of memory or stop sending them. And then the target that's actually attached to that will consume them and pull them out of the unbounded buffer. We can have an overwrite buffer, which is like a single value. You can send a message to it. Folks can consume from it as much as they want, but it just generates a copy, right? And you can reassign it a different value by sending a new value to it. And then, of course, single assignment, which is, for all practical purposes, a write once or a constant. Send and receive, which are template methods. So you can cooperatively send and receive the messages. And transform and call. So these are the more interesting ones, and these are actually the majority of the work of the imaging demo is actually built on these. So transform. When I get a message, apply a function to it asynchronously, of course, and return another message. And call. Just when I get a message, do something. And choice and join. So rather than using things like wait for multiple objects and wait for single objects where you're waiting on event, and then you have to go look up the data you're looking for, we can use choice, right? Where you can hook up a series of inputs and get the first one that arrives, right? Of multiple types. And then you can actually act on the thing you were waiting for. Or join, which will wait for them all. And there's a couple of kinds of joins that are actually interesting. So there's a greedy join, which would tend to consume everything as soon as it gets it, right? So if you have multiple of these together that are somewhat overlapping, you might run into problems there, but it can be very fast. Or we could have a join which actually waits for all things to be fired. It will take an offer of that message, and then once it has a full set of offers, it will actually commit them and make sure that it still has them. And if it can't actually get them because someone else has got them, then it will sit around and wait a little bit longer. This is very similar to what wait for multiple objects does. So here's an example. Very, very simple. So this is This is a file parser, right? It goes through, I'm going to read a file line by line by line. Whoops. Well, I'm not at the end of the file. And then I'm going to parse that line. So the current line is called WSC line, and then I'm just going to parse it. This is serial. The interesting thing was this came out of a little application utility that I wrote where there was basically 1 second of I/O and 3 seconds of computation. I was using it to parse tracing files, things like that. But it was, of course, all serial and very frustrating to watch it. You know, on my quad-core computer, it was very nicely pegging one processor, taking a long time, except for when it was doing I/O. But let's do something else. So I'm going to use the agents library to actually overlap that I/O with the computation. So the first thing I'm going to do is I'm going to create a message buffer. So this is an unbounded buffer of agent message. So the agent message is just a little message type that has the kind of message and the payload, that current line. So I did that here with this new unbounded buffer. Now I'm going to create a parser agent. This is a class that I've derived. The next slide has it. So you'll see it. And I'm going to start the parser agent. And then most of the code looks the same. So I'm still going to open the file. I'm still going to wait for the file to end. But now instead of parsing that inline, I'm actually going to construct a new agent message and send it to that unbounded buffer. Once I'm out of the loop, I'm going to send an exit message saying I'm done. And then I'll wait for the agent to finish. So here's the agent. So it's a new class derived from agent. Internally, it's got a reference to an unbounded buffer, which I don't show it here, but I'm assigning it in the constructor. And then I have this run method. And this run method gets called asynchronously when you start. And it's just going to do a blocking receive on the message buffer. If it doesn't get an exit message, it will actually parse that message and delete it, right? Because remember, I allocated it. And I'm past a pointer. Once it gets an exit message, then it'll just exit, and the agent's done. So, very straightforward. And this worked relatively well in that little application I built. Yeah?
How does that make it parallel? That'd be great coupling.
Yes.
How does that...
Great. So, in more details. So, the highlighted send. Rather than parsing the code in line, I'm going to take this unbounded buffer, which you can think of like a queue of messages, except it's ordered, right? So we can maintain orderability. This is why I'm able to send exit to it last. I'm just going to send it to that. When I declared the agent, that actually started the agent, and the run method was declared as a task that's being run asynchronously, and it will run until it exits. And so now the agent is running, right? Because this is a while my message, and I'm getting it in this blocking receive. So I'm going to start this agent, and it's just going to sit around and wait for a message. As soon as it gets a message, the runtime, the concurrency runtime, can actually wake that agent back up. We can process it, and then we go back to the top of the loop, which is another blocking receive. That answer your question? Yeah.
There's only one thread, or one thread running that run, right? So
Yeah.
Those two processors?
Yes. Yeah. You could potentially further subdivide the parse, and the imaging filter, the imaging demo actually does this. This is just a very simple example. Transform and call work like this too, right? So rather than this agent, I could have hooked up a transform to it, right? And again, just like with the agent, there's only going to be one thing running at a time. So you have some thread safety there. So if I pass in a functor or a function or a lambda to that transform, I will only have one instance of that transform running, right? So I can still run it asynchronously. I can still light up the pipeline, but I can be more thread safe. Okay. So let's take our imaging demo, and let's actually make it scale. Let's remember the scenario. We're going to search a directory for files that are images. We're going to then load the images from the disk and apply the image filters. So in the parallel version of this, searching for images is actually a task, right? I just spawn a task to start traversing a directory using, find first and find next. Very straightforward. Once I find an image, then I'm going to send a message. In this case, I'm sending it to an alternator because my pipeline is very small, right? And we're running on a 16-way computer. And the filters aren't completely parallel. There's sequential versions and parallel versions of them. It's like that on purpose, right? To talk about something more real world than matrix multiply or a ray tracer or something like that. So that load balancing is going to send it to a series of transforms that are hooked up. What the alternator will do is take the first transform that's available and send it to that. The transform then is going to actually take that path and load the image from a disk using GDI plus image load. And then it's going to call the image filters, which have a series of parallel 4s in them. The image filters will then actually send messages to a shared buffer, message buffer. That message buffer, there's something linked up to that which will actually notify the display that there's work ready, and then do some prep work to render it. And then, of course, since GUIs are single-threaded apartment model, the GUI does a set of the rendering itself. So, all right. So, let's start with the reverse directory. So here it is. Whoa. This is my call to traverse directory. Here's the serial version. I'm incrementing my image count. This is the one place in the application where I actually had to take a lock. I'm doing an interlocked operation on the image count because it's potentially cross-thread. There aren't any locks in the rest of this application. It's all built with messages. And then I'm going to parse it serially with the current file path. The parallel version has two things that are interesting. First, it'll actually take that recursive call to traverse directory, and it'll actually schedule a task. Right? So I have this task group here, and so as I'm recursively scanning the subdirectory, I come across another subdirectory. I can actually schedule that for a task. So in this case, everything is local. But if I were, say, scanning a file share, right, or sitting in New York and razzing in here to Redmond, and from some internet where the connection is atrocious, there's some additional opportunity, and I don't want to just be blocked on that network call and that file traversal. And then here, instead of just parsing it in line, I'm going to send a message, right? So I've got this image buffer, this unbounded buffer of paths, and I'm sending the current file path to it. The file paths here are W strings. This destination file list is an unbounded buffer of type W string. Right? So all of this is templatized, completely works with your own types as long as you support copy operations. So once that happens, in the serial case, we're going to start this timer, and then we're going to load the path serially. I'm going to create this blur functor. Did you guys catch this auto here? Another new keyword from C++ OX that's in the CTP. So I'm going to avoid the type on this because it can be more efficient, particularly with lambdas. If I can avoid actually describing the type, lambdas can be incredibly small and very easy to execute. And then just a little template function to actually help me make this filter function. What the filter function does, it actually takes the GDI plus bitmap, it locks the bits for read access so that I can process them quickly, and then it will run both of these in sequence, the Gaussian blur and the glow filter. And then I run it after I've created it. And then I take that image that I've gotten and I actually send it along its way to an image buffer for updated images. That guy will actually, like I said, do some processing work and then invalidate the screen and cause a repaint to happen. So the network version of this is very similar. This load bitmap is actually a transform. Concurrency : transform. Right? It takes a string and it returns a pointer to a bitmap type. And I'm constructing it with load image from path, which is this. It's just a function, but it's the same one I used right here, right? Then I have another transform, which is my Gaussian filter transform. It takes a bitmap type and returns a bitmap type. And I'm going to construct that with this filter that I sent it. Right? Very simple. And then this part is critical. Now I have to connect the network up. So in these steps, I'm actually linking the targets together so that when a message is received by one block, it'll get propagated onto another, because until you actually do that, the messages will just kind of sit there and queue up. Right? You can send messages to it, but the network isn't actually alive until you connect them. It gives you some flexibility about declaring the network in one place or a block to it and actually connecting it at runtime. So I'm going to the load bitmap, I'm actually going to link the transform. And to the transform, I'm going to link this updated images buffer. So let's run this. It's a lot faster. It's hitting a big image right now. Like I said, some of these are 8 megapixel. A lot of the other ones are actually only 100K. These are actually relatively expensive filters. But even still, they're not completely parallel the entire time, right? I'm doing a parallel 4, and then I'm doing some sequential work in a parallel 4, right? So let's see how this does on the 16-way. Let's see. I got to remember the password. "191 seconds." This has a different set of images, but the ones that we saw before are actually here. Here you can actually see the glow on this one, right? On some of these astral photography images. You can kind of see it there in the windows. Wow. This took a little longer. Usually this gets about a 10x speed up. So I'm not sure what happened. But I'm going to run it again. Because... yeah. There we go. That's the same share that it was pointed to before. There we go. That's a little better, huh? 15 seconds. Great. Okay. So I actually saved a lot of time for questions here. When we look overall at Visual Studio 2010, on the managed side, we're looking at the parallel extension to .NET. Again, Daniel Moth is talking about that in just a couple days. On the native side, we have the concurrency runtime with the load balancing work stealing scheduler. We have the parallel pattern library for data and task parallelism. And we have the asynchronous agents libraries. We also have the parallel debugger tools and the concurrent profiler. Great. Okay. We have several more sessions. Hazem's talk was just a little bit ago talking about the profiler. We have Daniel's talk coming up. Nicholas will be talking in detail about how to actually integrate with the resource manager if you have your own scheduler or your own programming model that you want to interact with. And we have a series of symposiums from various folks on our team. So, great. Yeah?
What happens when you depend on the result of the agent or on a task?
I'm sorry?
So what happens when you depend on the result of a task or on an agent?
What happens when you depend on the result of a task or an agent?
Yeah.
So, dependencies are actually most easily expressed in the PPL and the agents library through agents, right? So I can say, I can take a transform, and if I want to run something else when something runs, right, I can apply a transform and then run a call, and that will link them. If I just have a series of tasks, I can actually call schedule things on a task group and then wait on them. If I have many tasks or many results, I can take a choice or a join, schedule them, and then wait on either one of those items or all of those items. Did that answer? Okay. You.
What I was thinking about was if you have to do, let's say, string searching.
Uh-huh.
So if you had to search for a number of different words, even 1,000 words on a given piece of text, if you spun this up, wouldn't you also get the benefit of hitting your cache much, much heavier? Because they'd all be running at roughly the same time, so they'd all be
Yeah,
in the
absolutely.
same area of data.
And the runtime will actually tend to keep things local, right? So if I have a series of components and a series of loops that are actually scheduled together, it will actually try to steal from a task or from a loop that's actually close to it, right? So if processor A has work and processor B just run out, it'll look locally first.
A lot of these processors share like third-level cache and stuff.
Yep.
So that'd be
Great.
too.
Yeah.
It looks like there's some operating system dependency in some of this stuff. So what's the minimum platform for this license?
So this is part of Visual Studio 2010, so we'll have the same, in general, requirements as Visual Studio 2010. There will be some restrictions, but we're clearly looking at, right now we're looking at Vista and XP, those sorts of things.
But when you, for runtime, I might compile that for that run on XP.
Yeah.
We're interested in Windows 2000 for base. That would be nice if we could tell our customers that.
Yeah.
But is there a chance that this will be supported on Windows 2000?
Nobody can
The CTP doesn't currently support Windows 2000. So, great.
Hey,
So, also, several folks from our team are actually at in the Microsoft Pavilion. We're sharing a booth with the HPC team, so we're there. If you want to come talk to us, I'll be there all night. Stephen Tobe will be there all night as well, who does a lot of work on the managed side. So, yeah.
So Visual Studio Design already supports OpenMP.
Uh-huh.
Are you going to provide a set debugging and profiling for OpenMP or just for the...
except there's the buzz. Don't wait for him to say. Just
So-
start talking.
So the question was, are we going to provide debugging and profiling support in OpenMP? So the debugger, the task view, doesn't work with OpenMP right now. The multi-stack view has a threads view, which will actually show you the threads that are going on, but it's not, at this time, currently hooked up to OpenMP. There is opportunity, and long term, we would like to actually ensure that the OpenMP implementation actually talks to the runtime so that your OpenMP parallel sections will actually compose with your other parallel sections in the application.
I get a couple of questions. Hold on. The first is, are you guys going to submit any of this to standards, or is this going to be a Microsoft Windows thing only?
So we care a lot about standards. That's why you'll see actually that the PPL interfaces are STL styled. Right? We care a lot about compatibility, and we hope that the community and the industry actually gets together and moves the standards forward. Right? We always talk to the standards committees about things, but we don't necessarily have a proposal right now for that. But we're very interested in standardizing work.
Okay. I have a couple other questions. Can I ask? The second question is, on a system that has hyperthreading, how does all this affect?
So the runtime is aware of the hyperthreading. At this time, we're not necessarily doing anything special for hyperthreading in the CTP. But the load balancing characteristics will actually tend to help with hyperthreading, right? So if I have, say, 4 threads that are showing up and half of them are hyperthreaded, those tasks will just appear like tasks that are potentially running slower. And the other threads will actually steal work from them. So the locality information is still preserved.
Okay.
But we're not necessarily doing anything special about it right now.
Now, on a single core machine, is there going to be any overhead of all of this?
Right, so there's always overheads, right? And
How bad is the overhead?
what we're trying to do is spend as much time at the platform level on reducing those overheads, because reducing the overheads is hard, and we would like to do it once, right? So that you guys don't have to spend your time doing that work. We'll do it. The overhead is continually getting lower. So, okay.
Are you going to release any source to the PPL itself?
So the
I saw in your stack trace.
Yeah,
there's
so
a lot in there.
So the PPL is actually implemented as a template header file right now. So crack open that CTP, pound include ppl.h, in addition to being able to actually use the constructs that are in the namespace concurrency, you can actually see how we did it, because the PPL and the agents libraries are built on top of the concurrency runtime.
Okay.
So
the concurrency runtime is kind of a symbols only thing then?
I'm sorry, I didn't hear that.
The concurrency runtime is a symbols only thing then? You're not going to have any source to that?
Yeah, right now there's symbols only for the concurrency runtime. It's actually part of the CRTs in the CTP. So the majority of the code is actually in MSV CRT for the binary files.
Okay. And on your agents example, are they actually built on top of the tasks, or is the agents pretty much map, the orthogonal to tasks?
They're built on top of tasks. So the runtime itself has a task scheduler, which is the abstraction for actually scheduling tasks. We have a couple of different abstractions at the runtime layer, and remember the runtime is extensible, so if you want to, you can actually build here. One is a task group concept that maps very well to the PPL task group. Another is a scheduler group. I believe it's actually called cast group in the CTP, but it will schedule what we call lightweight tasks or unrealized chores, and those will actually be run more in order than some of the other ones, which are clearly load balancing for the majority of the parallel fours and things like that. So,
okay. One last final question.
Sure.
Our current code base takes advantage of OpenMP in a number of areas. As we move to this, say, in 2010, and we have some parts of the code start to use tasks, your concurrency runtime talked about being able to manage resources more effectively, arbitrating between them. Is the OpenMP support in 2010 going to be, arbitrating between OpenMP stuff and task stuff to not over schedule the processors?
Yeah, that's not something that's currently that we can currently announce or talk about in detail at this time. The CTP clearly does not do that, right? So if you use OpenMP and you use the PPL at the same time, you'll see some oversubscription going on.
Okay.
All right. Come up to the mics so I don't have to try and choose someone in front until someone shows up at the mic.
My question was just, are all these sample applications on the drive?
There are not sample applications on the drive. There is a walkthrough, which shows how to use Parallel 4 and the agents library. There's also on our concurrency center, so msdn.microsoft.com concurrency. There's pointers to the forums and to the blog where there will be additional samples, and you can actually interact with us through that. So.
If I understood correctly, the message structures that you're using are leveraging the concurrent safety of the stack.
Mm-hmm.
Are there any techniques you're using to minimize impact of just beating on the heap with some of these functions and objects that you invariably have to create?
Yeah, one of the things we're actually exploring is some heap work to make sure that as you're using the heap, it just scales, right? And that would be at the runtime layer. It's not something that we would do at all. I think there's nothing in the CTP, and it's not something we would do in 2010 that would be globally applicable, but we're investigating that at the runtime.
Is it correct that it's single heap right now?
No, it's more advanced than that. This demo was actually using some of that on some of the things. I wasn't using it for the messages, but I was using it in the transforms. The Gaussian filters actually make a copy of the image, right, and process work in that copy and then apply it back. So, yeah, great.
I'm a managed code weenie.
Uh-huh.
So I just want to know the parallels, I guess, between this and the managed world. What the libraries that you have in managed versus this.
Sure. So the libraries in managed, and folks can step in if I miss something because they're here, I believe. So we have the task parallel library in the parallel extensions. This is also in the CTP. It's in the system.threading DLL. So they have a parallel for each, and task constructs. In general, many of those are actually aligned with our PPL interfaces. The core tasks, scheduling, and creation are slightly different, but this actually is more to do with the memory model and the lack of a garbage collector in C++, right? Because you want to be able to manage the lifetimes of those tasks, right? So I can just use a task group.run implicitly, or I can declare one explicitly, or I can create a new one, or I can build it with my own allocator, right? We have that flexibility and power on the native side that isn't necessarily there, and it led to a slightly different design. The native side doesn't. The managed side doesn't currently have a messaging framework. Microsoft has something called the Concurrency and Coordination Runtime, which is similar, and we'll continue looking at that in the longer term. So, okay? Yeah.
If we're using TBB now, is there any advantage or disadvantage to using this new mechanism?
Well, the advantage to using TBB now is that it's released, right?
Right.
And you have a CTP. Longer term, what you'll see is some alignment between TBB and PPL on the interfaces, particularly on the containers, right? So as you're learning to use TBB now, those learning skills will actually apply with the PPL. There's also the composability argument and the performance, right? So to the extent that future versions of TBB align with the runtime and interact with the runtime, using them together will actually compose, right, instead of oversubscribing.
So if we're using TBB in the future releases, when it does support the runtime, we'll be able to see those in the task window that you showed earlier?
It's unclear how far or how deep the integration will be. Okay. Yeah.
Can you limit, like in the current environment, you can create a job object and say, each thread takes up a mega stack, and say, I want to kind of limit the working set. Can you actually do that with the PPL?
You can,
right.
But not with the PPL.
Right.
You can do it with the runtime.
All right, okay.
So the programming model and the runtime are layered, right? So the runtime has rich support for multiple schedulers. So you can actually describe a scheduler, you can construct it. You can say, I would like n many threads, no more than n threads. I want to have oversubscription, right, if I'm going to do a bunch of latent operations that are blocking but still want that caching information. I can talk about the stack size for the threads that it creates. I can talk about the priorities. It's really an abstraction, right, on top of a background thread. Whereas in previous times, you would have used a background thread when you really had to, right, to do additional work. Now you would use a scheduler when you really had to and apply some quality of service constraints on it. The hope is that you can just compose things and not actually have to go to that level. But when you need that level of control, it's there too.
Just based on that, two questions. Does the job object still work? And are the threads dynamic? Like when you're not using them, does it?
Yes, they go to sleep. So the threads are still there. If we go to the imaging demo, and don't do anything with it once I've actually started the network. The threads are actually absolutely still there because we construct them once and we reuse them, right? But they're not doing anything. So, all right. Surely there's more questions. Yeah.
I'm sorry, how do you understand which threads should you assign to work if you don't see the threads created in parallel in your library?
So how do you understand which?
So you create basically the task,
Uh-huh.
you run it, and you open the task view and you see a lot of threads running in tasks. So how do you get down and let threads know which working sets you assign to them? Which thread is which?
Right, so you work with, so we've abstracted away from threads and tasks. You don't necessarily interact with the threads, right? But you can talk to a scheduler, you can construct one, you can apply a scheduler to a current thread, and so then any parallel work described on that will actually be constructed against it. You can also take that scheduler and build libraries or schedule tasks against it directly. But it's more, Windows-style programming, so it's not at the higher level programming model.
So basically you just create all the new threads in this particular fashion.
Mm-hmm. All right. Yeah. Books. I have books to give away. Folks have to ask me really good questions.
One last question on deployment. So the only dependency is a C runtime. There is no other dependency on the PPL. And since it's templated, I guess if you don't use any of the, you will need the C runtime. Is that right?
So if you don't use, so the runtime is part of the C runtime.
Yeah.
Right. If you don't use any of the runtime objects, it doesn't get invoked. Right. It isn't just on. You have to actually call a scheduler, call a parallel algorithm, do something like that. Otherwise, it's just, code just sitting there being latent. So.
Based on that, last question. Oh, on that book. Based on that.
All right.
Based on that, so do you, compilation with the PPL, you'd provide different libraries. So if you're using the debug version or the multi-threaded or static.
The PPL is a single header file.
All right.
It just works. You don't have to do anything.
All right.
Right. So.
You didn't show any samples for the schedule. Are they available online?
No, but I'll probably blog about them, and I can show one because I have some in code here. Let me ask his question here.
Just a quick one. I like the agent system you've got
Mhm.
on messaging. I presume it's thread safe, and I'm just wondering just kind of how robust it is. I can think of a number of applications where I could use something like that.
The agent's network starts out thread safe. You can, of course, break it. That's right. You can set up a network, pass pointers through it, use them all at the same time. Right? That would not be good. In my case, I'm sending transforms along, right? And it's okay because I'm not actually getting anything. So for the person who asked me about the scheduler, first I'm going to declare a scheduler policy right here. And I'm telling it, this is this create policy. It's very, very long. Sorry. I'm going to tell it how many properties of that policy I'm actually going to apply in. So in this case, I'm actually setting the priority a little bit lower in this app. And then I'm going to tell it how many threads I want with this min threads. So property, value. Property, value. And now what I'm actually doing, I can do two things with this policy. I can create an arbitrary scheduler with it. Or in this case, I'm creating the current scheduler. So this is the application's current scheduler, the one that's in use unless you've specified something else. So there is one scheduler per application by default. If you want to do something else, you can. That's right. This is about having multiple applications that are multiple components that are actually concurrent at the same time. That's for you. So this is one of our dev leads, Joe Duffy, just released this book. All right, so you had another question? Is it time to go? Okay. I'll be at the booth. I still have 2 books to give away.